We want to look at this question related to permutations, where we're given that we have a group of football players, 2 Americans, 3 Europeans, and 4 Indians, and these players stand in a line in a random. In the first part, we want to find the total number of arrangements possible, considering each player is unique. So, I'm sorry. So let's find the number of arrangements by players. So you want to find the total number of arrangements considering each player is unique. So in this case, how many players do we have? 3 plus 2, 5, then plus 4, 9. So this they can be arranged in 9 factorial ways. Because we know when we have an object of n, because when we have n distinct objects, then the total number of permutations of those n distinct objects is n factorial. So here we have 9 unique players. The number of ways we can arrange them is 9 factorial, which is equal to 362,880, because all players are unique. Right, so here we're just applying the fact that we have n distinct objects. The number of ways we can arrange them is, if we have n distinct objects, the number of ways you can arrange them is n factorial. And here we have 9 unique players, so the number of ways that we can arrange them is n factorial. Let's look at part B. What are total number of arrangements possible based on nationalities? So here, this was the number of arrangements by players considering the 9 unique players. But here we want to find in part B the total number of arrangements based on nationalities. We don't differentiate between the 2 Americans, we do not differentiate between the 3 Europeans, and we do not differentiate between the 4 Indians. So we want to find number of arrangements. So there is a difference between part A and part B. In part A, we're finding the number of arrangements by player, where all players are unique. Here we're finding number of arrangements by nationalities, where players of the same nationalities are considered indistinct. So this would be, now over here, the idea is this. So we have basically, this is right. So we have 2 Americans, we have 3 Europeans, and we have 4 Indians. So here we want to find the arrangements by nationalities. Are we treating the 2 Americans as indistinct? We're treating the 3 Europeans as indistinct. We're treating the 4 Indians as indistinct. So if you want to find the number of arrangements by nationality, so this will be 9 factorial divided by the 2 factorial permutations of A. Similarly, the 3 factorial permutations of E, and then the 4 factorial permutations of I to avoid double counting. So similar to how we find permutations or arrangements when some objects are indistinct. Because players, this is 1260. This is because players of the same nationality are indistinct. So the first part is like finding permutation. So part A, where you're finding the number of arrangements by players, where all players are unique. So here you're just applying the fact that if you have indistinct items, then the total number of permutation or arrangements is n factorial. Part B is also asking you to find the number of arrangements, but this is by nationalities rather than by players, where you're treating players of the same nationality as indistinct. So you have to divide by their own respective permutations in order to avoid any double count. So there is a difference between part A and part B. In part B, we're finding the total number of permutations where some objects are treated as indistinct, and here players of the same nationality are treated as indistinct. So you have to divide by their respective permutations. Okay, moving on. Part C says, what are the total number of arrangements possible if no 2 Europeans are to stand next to each other? So we have 3 Europeans, and we do not want any of the Europeans to stand next to each other. So there are 3 Europeans. So total there are 9 players. So excluding the 3 Europeans, how many players do we have? 6. 1, 2, 3, 4, 5, 6. Since we don't want any of the 2 Europeans to stand next to each other, so we will make sure, so we don't want any of the 2 Europeans to stand next to each other. So we'll make sure that these Europeans stand in the empty spaces between the remaining 6 players. So how many empty spaces do we have here? These are empty spaces. Right, so these are the 6, the dashes represent the 6 players other than the 3 Europeans. And because we do not want the 3 Europeans to stand next to each other, so we will make sure they stand in the empty spaces between the remaining 6 players. So this is the spaces where the 3 Europeans can stand. Right, so total, how many ways can you arrange these remaining six players is six factorial, right? One, two, three, four, five, six. So in six factorial ways, the remaining six players can be arranged. And then what you're going to do is you're going to choose any of these three spaces where the three Europeans can stand. One, two, three, four, five, six, seven. Out of these seven, we can choose any three spaces and then arrange the three Europeans there in three factorial ways. So we're doing selection plus arrangement. So we're going to apply 7 NPR, right? So how where does this come from? There are six factorial ways in which the remaining six players, other than three Europeans, can stand, and then we have seven spaces where the three Europeans can stand between the remaining six players. So we basically, out of seven, will choose any three spaces and then we can arrange the three Europeans in those three spaces in three factorial ways. Because we're doing selection plus arrangement, so we apply NPR rather than just NCR, right? Because we have these seven spaces, 1, 2, 3, 4, 5, 6, 7, where you can have these three Europeans stand, right? You can choose any three of these, and within those three spaces, you can arrange the three Europeans in three factorial ways. So this is for the selection plus the arrangement of the three Europeans in any three empty spaces. So this turns out to be 151, 200. Now let's look at part D. Part D is what are the total number of arrangements possible if the two Europeans are to stand next to each other. So we want the two Europeans to stand next to each other. So the two Europeans, we'll just put them in a box like this. And remaining, how many players do we have? We have remaining seven players left. 1, 2, 3, 4, 5, 6, 7. Right, so the total, so basically the two Europeans are always going to be considered as one lump, like this, right? You're going to lump them together like this, so they're considered as one block. So total, how many now, how many ways can we arrange these? Is 1, 2, 3, 4, 5, 6, 7, 8. So we can arrange these in 8 factorial ways. Total 8 blocks like this into the two factorial arrangements of these Americans. These Americans can be arranged within each among themselves into two factorial ways because being two different Americans, we can arrange them in two factorial ways, right? It could be like, so there are two factorial permutations of these Americans. So this is 80640, right? So over here, we wanted the two Americans to stand next to each other, so we lumped them together like this, and then total, and meaning we have seven players, so together so we're arranging in 8 factorial ways. This. And then these Americans can be arranged in 2 factorial ways.